The lesson today is talking about the mean value theorem and how it applies to both derivatives and integrals.
At the end of the video, you will be asked to do a comparison of the application of this theorem graphically, numerically, algebraically, and verbally to both derivatives and integrals. Let us begin with reviewing the mean value theorem for derivatives. The mean value theorem states that if a function is continuous on a closed interval and differentiable on an open interval, then a derivative exists at a point C on the function, such that the derivative is equal to the slope of the secant between points A and B. This is an existence theorem. Looking at this example, we can numerically and graphically demonstrate the mean value theorem for derivatives. The function y equals x squared is continuous on the closed intervals 0, 2, and also differentiable. At c equals 1, the derivative is 2, and the slope of the secant line, AB, is also 2. The instantaneous rate of change is equal to the average rate of change. Now let's look at a periodic function. If the average rate of change between my 2 points is 0.0483, I now have to find a point C on the function where the derivative at C is equal to this slope. I can see that it exists, but I'm having a very difficult time securing it. Since this function is periodic, I can graphically demonstrate how there can be more than one point C where the derivative is equal to the slope of the secant AB. Does this function meet the conditions of the mean value theorem? A resounding no echoes from the audience. This function is not continuous. The points A and B are located on two different pieces of this discontinuous function with a slope of 0.7634. As you can see, the derivative of both pieces of the function is 0. The derivative will never be 0.7634. The mean value theorem for definite integrals must also be continuous on the closed interval. There is a point C on the function such that f of c is equal to the average value of the integral. Remember, integral over interval. Graphically and algebraically, let's gain a better understanding. The value of the integral f of x is the area between the function and the x-axis. The mean value theorem states that there exists a value f of c which represents the height of the rectangle, and when multiplied by the interval will be equal to the definite integral of the function on that closed interval AB. For the function y equals x on the closed interval 0, 2, there exists a y value that is the average value of the integral. Now I can move the y value and shade the region on the closed interval to estimate the integral. The y value will represent the average value. My estimate was a little low. The value of the integral is 2, and the average value is 1. For the function y equals x squared on the closed interval 0, 2, there exists a y value that is the average value of the integral. If I were to visually estimate the integral, then I would say that the average value is approximately 1.5. My estimate was a little bit high this time. The average value is 1.33 with an integral value of 2.66. The next function is a cubic on the closed interval 1, 3. If I were to visually estimate the integral, then I would say that the average value is approximately 2 with an integral value of 6. My estimate was quite low. The actual value is 3.375 with an integral value of 10.125. Was your estimate better than mine? In estimating the average value of this function, it appears to me that the region above the x-axis is larger than the region below the x-axis, so I'm going to estimate the average value to be 0.15. I was much closer this time. Your task now is to compare the mean value theorem as to how it is applied to both derivatives and integrals. Similarities. First, record all the similarities in applying the mean value theorem to both derivatives and integrals. It is because of these similarities that we frequently confuse and misunderstand its application. Yes, I want more than 2 similarities recorded. Now, differences. On the left column, you will record specific characteristics of application of the mean value theorem to derivatives. And on the right column, you will record characteristics specific to definite integrals. For conditions, what are the conditions specific to each concept? Which concept is connected to average rate? Which concept is connected to average value? What is the algebraic representation of the mean value theorem for derivatives? For integrals? And last of all, select an example and solve it. Not one that I've used in this video, but apply that example to the mean value theorem in regards to its derivative and integral. Explain your solution numerically, graphically, and verbally.